Hello again, this is Grant Swartzwelder, and welcome to another episode of Oilfield Strong. You know, over the last year or two, there's been more and more conversation about nuclear reactors, how that's the kind of the panacea for energy issues. A variety of different types of nuclear reaction. Fission has been one of the most used, most accepted, but you always hear about fusion as kind of the answer to it all because of what our guests will be talking about shortly, how it can really kind of be almost your own little plasma sun that will just generate energy and has a lot of advantages, but I think it also has some challenges too. Well, today to talk about that, I am so fortunate to have Dr. Michael Ginsberg. He is president of Tokamak Energy. Michael has 20 plus years of experience advising universities, private sector, public sector, all in the sustainable energy area. Has joined Tokamak years ago to help them roll out their U.S. Activities. And with that, it seems like he's done a great job because I need to read this because it's important enough for me to actually get it right. He was one of 8 companies for the Department of Energy's milestone-based fusion development program. I don't know if that's a big deal or not, but it sure sounds like a big deal, and I bet Michael will help us with that. So, Michael, welcome on board, and appreciate you joining to. Now, remember, I am just a dumb little Texas oil guy, so if you need to use pictures or dumb this stuff down, that would be great for me. But some of the other people that'll be listening will probably actually understand what you're talking about. But so let's start with just something kind of more broad, and then we'll go narrow it down. Talk to me about fusion as a whole, but Tokamak Energy also and how they're tackling it, because obviously they're very linked.
Yeah, well, Grant, thank you so much for having me. It's a real pleasure to be on the show, and happy to talk. And I think you actually nailed it when you talked about the sun in a bottle. I've got behind me the inside of what our fusion device looks like, and I'll explain that in a bit. But yeah, I think you explained it quite well. You know, fusion is really a step change in energy in the way that people use and produce energy, and so it is a form of nuclear energy. It's, in my view, really that most advanced form, and very energy dense, very clean when it comes to radiological issues, and so we're rapidly working to commercialize that energy now, that technology. Tokamak Energy has been around for 17 years now. We're one of the oldest fusion energy companies in the world, headquartered in Oxford, England, and have been in the U.S. for about 6 years, working really across the U.S. ecosystem with national labs, with universities, to advance the state of the art in fusion technology. So our particular technology has been what's called a spherical or a low aspect ratio tokamak. Just to break that down, what you see behind me is basically you can think about it like a magnetic cage, a cage that traps really high energy in a small space so that we can create the conditions essentially that are fusion, what you see in the sun. And it's a really challenging technological feat to make this happen. It's why it's taken so long to commercialize. But I think we are rapidly getting to that point because of a lot of the underlying technologies that have been developed over the last several decades. So we're really excited about our strategy here in the U.S. We think that the U.S. is going to continue to be a leader in the nuclear sector, and we're very excited in particular about Texas and the position that Texas can play in the advanced nuclear and fusion space.
Well, let's talk about that because we actually met at Texas A&M at an event down there. I know they've been really pushing it, but it does seem like the Texas government and the academia here has really been pushing that. I remember when I was a student at A&M 30 years ago, nuclear department had like 5 people in it. So, and it has grown significantly more. So what's happening in Texas, and how does that affect a company like yours in growing?
Yeah, well, you see across the U.S., not only exploding demand from, AI data centers, but also you've got aging infrastructure. And so states, especially those like, Texas, are seeking energy security, seeking firm power, baseload power to meet reliability goals. And, the governor, under the governor's leadership, has identified advanced nuclear as a key technology in the mix of multiple technologies that Texas has been spearheading in order to ensure that security. And so, you've got fantastic pilot projects now at places like Texas A&M that are coming up at the Energy Proving Ground at Rellis campus. You've got a number of other nuclear projects that have been announced in Texas. And so really under the leadership of the governor and also the legislature, there is now a clear direction in Texas to be a leader in advanced nuclear. We think that really the forefront and the most advanced is going to be fusion, and Texas is well positioned to be a leader in this technology as well.
And so what is Texas providing? Just regulatory, or is it financial? And I know there's also, like the Department of Energy program that y'all were awarded, that I assume that had financial, so to help me understand how academia, how government, state, local, national, what are you looking for? How does that relationship really need to work? Because clearly this is a very expensive, a very technical type thing that you're pursuing.
And it's going to take a combination really of the private sector and the public sector in this, across the industry to get to commercial reality. So, the private sector has a number of companies that have popped up in the last, 15, 20 years. And we, as you said in the beginning, are one of the down-selected companies that are a part of this Department of Energy program to commercialize fusion. We're really proud of that. Out of 50 companies, really, we're one of the 8. And so in addition to the private dollars, you have a strong Department of Energy program. Now under this current administration, we have the creation of a new office dedicated to fusion energy. And so that's a strong signal. But more dollars are needed to complement those private dollars. You look at globally, countries like China that are actually taking a lot of what we've put forward in our roadmap and putting the dollars behind it. And so federal support, as well as state support to complement some of the federal programs. So companies like ours are looking to leverage all of that to realize some of the facilities, not only the pilot plants and eventually commercial plants, but the test stands to de-risk some of the technologies. As you said, this is an expensive technology to develop, but when we do get it running, it'll be, in our view, the best option for baseload power.
I had a chance to go to a nuclear reactor down on the coast, and it was all analog, and they were talking about how long it would take to for permitting and changes. And there's been conversation about permitting as a issue for energy, oil and gas, which is where I locate, but in a variety of others. Have you seen an improvement from that standpoint on how the government, from a regulatory, from a permitting, has that advanced, or is that still, because that seems like a huge issue? It just takes a lot of time, which means a lot of money.
Absolutely, and that's a key advantage of the fusion sector. I will say that there's been some revamping of the Nuclear Regulatory Commission's procedures around fission technologies, but very notably, in 2023, the NRC announced unanimously that fusion energy would be regulated in the U.S. under the same regulatory regime as particle accelerators. So you can think about this as a very different risk profile. Essentially, we're dealing with radioactive issues that are in the lifespan of 12 and a half years versus hundreds of thousands, if not millions of years. So there's no long-lived radiological waste with this, and the NRC has recognized that. So in addition to that, what does that mean from a permitting perspective? If you look across the U.S., these projects will be permitted much quicker. Texas is a NRC agreement state, meaning that, Texas signed an agreement with the NRC to regulate, radioactive materials within its state. And so that means that the ultimate authority goes down to the state, in discussion with the NRC. But in summary, fusion essentially is in a similar category as a hospital. That's the type of radiological profile that we understand very well and we know how to deal with.
Now, from the novice standpoint, hear that and I'm like, ooh, should it be? That hospital sounds, you know, mainstream and all, and nuclear and fusion sounds scary. So help me with that. Is that I should be okay with that, I think.
Yeah, so essentially it just goes back to the process. Whereas with fission, we're dealing with heavy atoms like uranium, and that's splitting those heavy atoms to produce energy. With fusion, we're taking light isotopes of hydrogen to start with, and those include deuterium and tritium. Deuterium is basically the isotope of hydrogen that exists in seawater, so pretty not an issue. Tritium is the radiological one that has a half-life of 12 and a half years. But that's something that can be managed on site quite well. We don't need to store it, in Yucca Mountain or wherever for hundreds of thousands of
Really?
years.
Okay.
So I think that's an important point just to understand. It is nuclear, but it has a very different profile. It is short half-life. These are things that we understand how to deal with.
Well, and that point, one of the things in my research, it sounds like fusion, the waste component is a lot more favorable than some others, especially like light water. Is that right? And it kind of, I think, dovetails with what you were just saying.
Exactly, yeah. It's just the fuel is entirely different. The other important point is you might, people, when they hear, oh, you're dealing with 100 million degrees, that's what, is inside of this tokamak. You don't have any kind of risk of a meltdown reaction with a fusion device. Think about it as, your heavy atoms, the uranium and fission, they continue to split. And then there's that risk of a meltdown or runaway reaction. With fusion, the minute the energy ceases to go into the reaction, just dissipates. There's no potential for a runaway. So it's just a very different situation.
So I might be naive here, but you say hospital and fusion and they're about the same. Help me understand how that can be, and that the safety and that they should be treated the same.
Yeah, so essentially, when I mention hospital, we're talking about, in a hospital, you have different radioisotopes that are used for treatment and cancers and things like that. In a traditional fission reaction, you're dealing with really heavy atoms like uranium. Those atoms have a really long half-life, so long, time where they can be toxicological to people. And so with fusion, though, you're taking really light isotopes of hydrogen. So, mostly coming from seawater. You've got deuterium and tritium. Tritium has a half-life of about 12 years. And so it's very similar to the types of things you'd find in a hospital. The other part of this that's really important is, whereas with a, fission meltdown, there's a possibility of a runaway reaction, splitting those atoms that can continue. Whereas in the fusion reaction, the minute your energy goes in and ceases, you're gonna have a dissipation. There's not going to be a runaway reaction possibility. So the physics is very different, along with the fuel itself.
Okay. Well, let's talk about that fuel, because that seems to be one of the challenges, is that, and tritium in particular, where the amount that that exists out there, or how it's generated versus how much you need. And then you compound that with a short half-life, which helps you on a safety standpoint. But if you're trying to use it, that I assume the shorter half-life means you need more, and it kind of works itself into that cycle of how do you get enough tritium to perform. Is that an issue, or how's that being attacked?
Yeah, great question. And this is where this is an opportunity where there's some overlap with the fission and fusion communities. The use of tritium actually is a product of the fission reaction, and so tritium is an input in the fusion reaction, and you need, for a startup, essentially about 2 to 5 kilograms to start your device. But the important point is that's not an ongoing need, because the fusion reaction actually also produces tritium. So the idea is you get a tritium breeding ratio, or you get to a point where you're self-sustainable. So yes, we have a limited supply of tritium today. It's mostly with the existing nuclear fleets like the CANDU in Canada. And so you're going to need that to start. But essentially, the fusion reaction will produce tritium and thus will be self-sustainable.
Okay, so that's not as big of an issue, it sounds like. So the other thing that jumps out is that the temperature and the 100 million degrees or whatever you just said, that how is that generated and how is that controlled? Because that I don't understand how there's enough metal or substance to keep that contained.
Amazing stuff, right? It's as close to magic as I can imagine. So it's really quite amazing, because what again you're doing is creating a sun in a bottle. But this gets to our other secret sauce, and that's primarily the magnets. So you contain this energy with the use of magnetic fields. And it wasn't really until the 1980s, actually, a Nobel Prize winning discovery around high temperature superconductors in Texas, actually, that this material was discovered, that then we have now developed and made into a usable material for containing high energy plasma. So actually what you see behind me is the center column of a tokamak. And then around you'll have magnets as well. So you've got a center magnet and magnets all the way around, and that's going to essentially contain and shape the plasma. So the bit that you really can't even see in the center is the hottest area, and that's the part where you're tightly controlling it. The other parts of this is because of the magnetic fields, your temperatures on what's called the walls, or they call it the plasma facing parts are going to be a lot lower temperature. That being said, you need new types of metals and alloys. We do know that those exist. These are types of alloys like vanadium and tungsten that can withstand, these conditions. And these are also things that our team has been developing, and we just need to continue to produce and then test these materials under the conditions that you would see in a fusion reaction, which is exactly the types of things that we think a university would be incredibly invaluable at advancing. Places like Texas A&M or others across the country with that expertise and materials, to then have a facility to essentially test those, to de-risk it for the private sector ultimately, and for commercial power plants.
So you are telling me that this is science and it's not just sorcery. That's the creating, because
there's no unobtainium here.
I'm sorry.
They call it unobtainium as an element, as in a joke around an element that doesn't exist. We're talking about things that exist. Okay. They are different compositions of metals and alloys that need to be tested.
Okay. All right. Well, I'll believe you on that. It's again way above. But so let's talk about kind of more the business aspect, and say, help me understand why fusion, and I assume, it seems like when I talk to various nuclear folks, that they want fission, they want everything to be successful, and there's a place for it all. But help me with the pros and cons between fission and fusion, from a challenge, from an opportunity. Kind of how do I compare those two?
Yeah, and I think we touched on a number of the points. Fission, has been a technology that's been around for a while in terms of operation. We have commercial fission plants that exist today that have proven themselves out beyond first of a kind demonstrations. But on the flip side, you're again dealing with a waste issue, a long-lived waste issue. And you do need novel technologies to address those. You're also dealing with the risk around permitting, which again, hopefully the technologies are starting to address. But again, the NRC has historically been a huge blocker for projects in the US. You talk about some projects in China that are using new technologies, but they've accelerated beyond us. Now, you look at fusion, Fusion, again, is a technology that's been explored, understood for a long time. Very challenging on the engineering now. We've got a lot of engineering work to do, as we discussed, around materials, around life cycle tests, and so from a regulatory perspective, it's a lot a lower burden because we're dealing with much different order of magnitude of toxicity. But on the downside with fusion, you're dealing with a technology that needs to really prove itself out at a first of a kind and ultimately at a commercial scale. Economics wise, I love looking at the numbers. We see a path where, fission and fusion are both going to be very low cost, baseload, affordable power, which is exactly what ERCOT and, different ISOs in the US need to do for ratepayers.
But that's on the ongoing kilowatt standpoint. The cost is really the upfront and the capex, right? And it's
And
right. Significant.
Yeah, so both for fission and for fusion, that upfront cost is big as you compare it to things like solar or wind.
Right.
But what you're going to see is, and what utilities really care most about, isn't just that number of dollars; it's that number divided by your kilowatts. So what's your normalized capex? How much do you get per kilowatt of energy capacity? And on that front, you're very competitive. You're increasingly going to be competitive with things like natural gas as you develop this technology out. And that's the pathway that we've charted forward. And I should mention, you talked about that DOE program. We actually just completed our preconceptual design that is currently the DOE is finishing its validation of. But basically, our design is charting a path to what is going to be commercially relevant. What's that capex per kilowatt and that cost of energy that's going to be really going to be very important for ratepayers and for American citizens.
When you talk about the cost of the kilowatt going forward, I also worry about like the heat or the temperature issue, and does that generate a lot of cost to maintain? But at the same point, it seems like that heat that's being generated, again, has a lot of, you're creating energy, but you're creating that heat. Seems like that's a lot of, there's a lot of positive associated with that too. So it's a double-edged sword.
That's a great point. Obviously, there's heat and then there's heat. I've learned in my experience in engineering, but basically there's high-grade heat, low-grade heat, and you talk about the industrial sector. And we've talked to some of the, your background, the oil and gas companies in Texas and, across the US. And they're looking at things like hydrogen, to offset, some of their natural gas use. And so we could see waste heat essentially being useful for some of the industrial processes in the oil and gas sector, 100%. Now, obviously, cooling is always going to be there, but there are ways to reduce water consumption around cooling. You look at open loop or open or closed loop cooling processes. But essentially that thermal energy is the first product that comes out of a fusion reaction is the thermal energy. And then that thermal energy is converted into electricity.
Okay. I think, and again, correct me if I'm wrong, which I'm sure you will, but it seemed like fission, they need all this water, light water fission to cool it off. It seemed like there's a lot of extra that is needed there. Is that the case for fusion? Is it a big user of water for cooling?
Similar profile.
Okay.
What we're dealing with though is again, it's all about how you manage that water. We're not talking about submerging the reactor. We're talking about a closed loop to cool it. We also have other types of fluids like glycol, for instance, to reduce water consumption. I actually was developing some hydrogen and ammonia plants in the state of Texas, and it doesn't, compare to some of the water consumption that we were looking at there. But water, we'll face it head on. That is a key issue across the U.S. when we look at water consumption, whether that be for nuclear power plants or for data centers.
Yeah, no, I think that's the hidden thing out there of the amount of water for, like you say, for data centers, for everyone, and that's going to possibly cause an issue at some point with all of this growth. It seems like. What I know there's clearly others doing fusion. Explain to me the business of all this. That there's I saw 7 or 8 different names. There's probably more, but is it gonna be a first to market type of thing, or there's just so much out there that more the merrier? What's the business aspect of all that? Do you need to worry about these others, or the market's so big it doesn't matter?
That's a fantastic question. I look at other industries for examples of where this one will head. And you've got some interesting examples from a economic financial perspective of where these companies are headed. And one fusion company is just announced they're going to go public. Another one just merged with the TMTG, the Trump Media Group.
I thought
I think you're starting to see the maturation of an industry from the startup space to a very diversified collection of specialized companies. Ultimately, you look at some of the bigger companies like Westinghouse or any of the big energy majors. I think they're all going to have their own, in my view, their own division focused on nuclear and fusion. And so some of the startups I think will become technology companies that will be licensing that technology. Like a manufacturer of equipment or an OEM. Some might vertically integrate and become an EPC or engineering procurement construction company. But I think ultimately what you're going to see is there's going to be a place for everybody. There might be some M&A activity over the next few years. There are a plethora, especially in the U.S., of companies, and so there might be some consolidation there. And so everyone's going to, find a seat at the table one way or another.
And do each of those have the same basic technology that using these magnets and the Tokamak type system, or is it fusion has different types of technology?
That's a great question, and not at all. There's a wide variety of different technologies, which
Okay.
is why I think that the base case for investors is really, underlying this is a lot of the subsystem tech. For us, it's the superconducting magnets. So we actually have a unit of our business that is providing that technology not only for ourselves and for other fusion companies that use magnets, but also for other sectors, like the space sector, and that's important in Texas, like data centers. We have a group that's developing superconducting data centers to make them more powerful. But outside of that, you've got a wide variety. You've got technology, you've got fusion companies that have, power electronics. You've got companies that make radioisotopes for medical treatments like cancer treatments. The list goes on and on. You've got defense applications. So some of the companies, the other major approach outside of the magnets is using lasers. So you can use lasers to compress a target of fuel. And that essentially is what we did at the National Ignition Facility lab out in California. And what they did was they just trained a whole bunch of lasers on that target. And you can just imagine the defense applications of really powerful lasers. And by the way, I mean, that's a main point that I talk about when I'm, talking to legislators in Texas and in Washington is the underlying technologies that you're seeing coming out of fusion are really critical for U.S. national security.
I tell you, you are getting closer to sorcery now that you're talking lasers even. So or it makes my little 5-year-old comic book mind just go crazy with all that. So, but again, I'll accept that for that. Well, help me. I guess one of the big, I don't know, negatives or the things that whenever you talk of fusion, you talk about that it's going to be a long time out, that the challenges. Give me an idea of the timeline for this and how kind of what the roadmap looks like for Tokamak or for fusion as a whole to be a viable in the field energy producer.
You can imagine I get that question a lot.
Yeah.
The main thing that I tell people is that, fusion technology or fusion energy has been a phenomenon that has been understood for quite some time. From a physics perspective, we know that it works because it's the sun, it's all the stars. We know how it works. We just know that it's challenging. And from an engineering perspective, we need new types of materials like we talked about, as well as we need to be able to control the energy in a very finite way. So think about the other things that have been happening in our in our society in the last 30 years, we now have some of those underlying technologies. Talked about superconductors as one key one.
Sure.
Before superconductors were around, there was no way to pump thousands of amps of current through a device to contain that energy. So it was theoretically possible, but it wasn't physically possible. Now, and the Department of Energy, is very keen on fusion and also on AI, has identified fusion energy as a lighthouse issue with the advent of AI. And this is something the Department of Energy has identified, is that AI can be leveraged now to control the energy, the plasma energy, in a way that we haven't been able to before, on an ongoing basis, on a real-time basis. So you've got companies like NVIDIA now doing digital twins of fusion devices. And so there's a whole lot of new enabling technologies that are going to now give rise to commercial fusion. And in terms of a timeline, yes, there is a lot of money that's needed to get this off the ground, but I see a groundswell of that interest and support, that we are very close to certain milestones being achieved scientifically. And so I think that we will see in the next decade some of these first of a kind plants.
Yeah, that's, when your answer, and then I think back to what you said, that some companies are going public, and this might just be my editorializing and you might not want to respond, but to go public with something that is still not quite sure what the timing is and the amount of capital, that'll be interesting to see how that plays out. So, thus to your point about potential M&A opportunity, but again, you might just want to nod and not, or if you want to respond, you're welcome to, but it's
Yeah, it's a great point. And I can't speak to those companies, of course, but I think they would say that liquidity is good, and liquidity is what is needed for that kind of capital injection is what's needed to advance certain milestones. I think it's a net positive for the industry. Obviously, what you're alluding to is certain patient investors wanting to have their exit, but this is natural for a VC life cycle.
Yeah. So when I was doing research, I heard that they talked about challenges being physics, engineering, and economics. Those seem to be the three buzzwords, and it seemed like the physics, y'all kind of got figured out, and that's what this read. But the engineering and economics might need a little more work. Respond to that. How far off am I, and where are the ones that if you stay awake at night, what subset of that do you stay awake at?
Great question. So, you can't ask that of the physicists, but I do think the physics is fairly well understood. I won't say that there's not. Yeah, I won't say that there's not still some questions, because you need to run these in operation. I think the thing that keeps me up at night is ensuring the sort of the probably on the engineering side, the materials can withstand certain conditions. That's getting to the need for test stands and facilities. So you need to do what's called accelerated life cycle tests, basically to know that these materials can withstand the conditions necessary. Because ultimately, if the physics and the engineering, you got the check marks for both, we do know that the economics will work.
Again, I'm thinking through the whole timing. Is that and again, back to Tokamak. So do you see when do you see a test reactor out there? Do you have any idea of, are we talking 1 year or 10 years or?
Yeah, like I said, I think sometime in the next decade, you're going to see these first of a kind or pilot plants turning on, showing really key milestones like getting energy out, testing some of that energy, getting onto the grid. I think there's a need to show it for a relevant amount of time for utility, to get comfortable. We've had a lot of conversations with utilities about that. But, every company has different timelines, obviously. But I think right now we're at this precipice of near commerciality. I'm not going to say there's not things to work out, but it's really up to us. Always, as always, the timeline is up to us. There's a famous quote from, I forget who now. It was a famous physicist who said, fusion will be ready when society needs it. So we're all banking on the fact that society needs it now.
Well, and we always say that in the oil industry, that we might be out of $30 oil, but there's $70 oil. So it's all dependent on how bad you need it and what the commercial, the economic aspects. One question about the commercial, do you see this, is fusion meant as a standalone, say, for an AI center, or is it meant to be part of a larger for utility where it's a baseline of electricity and energy? How does it fit into the whole spectrum of power?
You know, that's a great question, especially in the context of this proliferation of data center build out.
Yeah.
You see a lot of hyperscalers, tech companies planning to acquire their own generation.
Yep.
There's been a push from the White House on that. I do see the potential to co-locate some of these data centers with fusion or fission facilities. Certainly that's what the plan is in Texas. I also see the potential to alleviate some of the capacity issues on the grid by providing baseload power. Economically, what I will say is that the larger you get with these, the better the sort of units of importance get when it comes to low cost power. But that's early stage. I think you can see smaller scale devices, absolutely, but they're probably going to be more costly long term for the ratepayers. But for a company that will pay a premium for reliable power, 100% having a behind the meter solution.
So there is a modular aspect to this. It's just kind of because of the fixed cost, kind of a per unit economic effect.
Our analysis is showing that exactly the economies of scale from going bigger. That's exciting to us too, because this is going to now start to compete with existing technologies. Like ultimately, there is a path to natural gas costs, to even coal, essentially. But I think the downward pressure on the industry to co-locate and to avoid some of the grid and interconnection issues is valid as well. And so speed could also be speed and small is also a valuable thing for these data center projects.
Very good. Well, Michael, this has been fantastic. I read about fusion, never quite understood it. You've been very, very helpful in doing that. It's amazing how much the technology has improved, and listening to you makes me really believe that we are a lot closer than I would have ever thought, and it seems like it's got a lot of advantages to it. So thank you for coming on the podcast, explaining Tokamak and fusion as a whole, and I wish you the very best in getting this technology developed.
Thanks so much, Grant. I appreciate you having me on, and I look forward to bringing fusion into the Texas energy mix.
There you go. Well, thanks everyone for listening in. If you like what you're hearing, please follow us on YouTube or wherever you're getting your podcasts, and tell other folks and forward this as we expand our community. But thank you for joining us on this podcast of Oilfield Strong. Take care.